Okay, welcome back. We're continuing 4.1, the graphs of polynomial functions. We're gonna talk a little bit more about the parts of polynomials that tell us what we're looking at as far as what the graph looks like. So we're talking about end behavior, and end behavior is important because it tells us what happens as the function approaches negative infinity or infinity. So if we looked at the graph and we just kind of traced the graph all the way to the left and all the way to the right, what would they look like? So here's a little hint. The function behaves like the leading term. So let's look at this example here just to show how these two functions, the end behavior, are very similar. So notice this one. This function is a lot more complex than this function. There's the plus 3x squared, the minus x, the minus 1. But notice that the leading terms, right, the highest degree leading terms are the same for both of them. So let's see what happens if we're to graph this out. And let me write this down so that we don't have to keep going back and forth. Okay, so let's look at Desmos again. Desmos is super handy. It's good to have open if you just want to mess around with it as you're doing your work, because it tells you a lot of stuff and it graphs instantly, and you can just go ahead and point on little points on there and it'll tell you exactly where the intercepts are, mins, maxes, all that stuff. It's right on top of your graph. So let's graph the first one, 2x to the 5th plus 3x squared minus x minus 1. Okay, so you can see it's pretty squiggly there, right? Let's do the next one. Let's do y equals, and we said we're just doing the leading coefficient, so, or the leading term, so 2x to the 5th. Now, these two don't really look very similar. They kind of look alike, but they don't look similar. But because we're talking about the end behavior, when we're pulling this thing out and getting further and further away from the middle, you can see that these two things eventually look exactly the same till they're overlapping, right? So at close view towards the center, yeah, well, that's not very close together, but as we zoom further and further out, we can see that they become pretty much the same graph as we head to the left and to the right. So that's a cool little note about the polynomials, that the end behavior looks like the leading term, right? So one thing that we know is that the degree of our polynomial is going to tell us a few things. So if it's an even degree, right? So if our exponent, leading exponent, is an even number, then we're going to go, it's going to look like a parabola towards the ends, right? So if it's a positive for our a, it opens upwards. If it's negative for our a, it opens downwards. And then any odd degree, just like a linear function, right? A linear is x to the first power. It's going to look like that towards the end. So if it's positive, it goes from decreasing to increasing, or it doesn't go from decreasing to increasing. It steadily increases from left to right. It starts negative, it goes positive. And then if our leading term is negative, it'd be flipped upside down, and therefore it'd be decreasing from left to right overall. Okay, so it tells us the directions of our end behaviors. So let's go ahead and analyze and graph this thing. So we can kind of sketch it. We can also check it using Desmos, but whichever way you feel more comfortable. So let's look at this. So end behavior. So we have to figure out our degree for end behavior, right? So we're going to say that, okay, we have this squared and our x. So we have an x squared, but we're also going to multiply this with our 2x. So that would be 2x cubed. Right? So again, we take our parentheses, we're going to square our x part, right? We're not worried about the rest of it. We're just worried because we're talking about end behavior, about our leading coefficient. Our leading coefficient here, if we multiply the x minus 3 by itself, we'd get x squared. And then we'd multiply that with the other x here to give us our biggest degree. So x squared from the right-hand parentheses times 2x gives us 2x cubed. All right, so what that tells us is, well, our degree is odd, so our end behavior looks like odd, positive, because our term is positive. If the two were negative, then it would go in the opposite direction. It'd go decreasing. All right, so we're just going to draw our end behavior here. Now we're going to look at our intercepts, right? So our x-intercept, well, we'd have to solve this. But what I know is that if I take a negative 1/2, half of 2 is -1 plus 1 is 0. So x is going to be -1/2. You can solve it out if you want to. You could say 2x plus 1 equals 0 and solve it, but you'd come out with the same thing. And then for the second one, we'd have 3 because 3 minus 3 is 0. Okay, for our y-intercepts, we plug in 0 to our into our x, right? So we said that that's f of 0. So if we do 0 times 2, that's 0 plus 1 is 1. And then if we plug in 0 to the second one, we get 0 minus 3, which is -3 squared. Okay, so -3 squared is 9 times 1 is 9. Okay, on our multiplicity, so where we have 1/2, that's multiplicity 1. So we know it's going through the graph at -1/2. The second one is 3. And because our multiplicity there is 2, we know that it's going to bounce. Right, so things to note here, even though it's not asking you to do it. So let's kind of graph what this would look like. Let's just draw a rough graph from what we know already. Okay, so we have a y-intercept of 9. So I'm going to mark that. Doesn't matter exactly where it is. We have 1 0 at -1/2. So we're going to mark that. We have another 0 at 3. All right, so we marked everything in there. Now let's talk about end behavior. So we know the end behavior looks like this. So let's change colors here. Let's do orange. So I know that coming off of here, it's going to look this way, right? Because that's this side of it. So we start on the left 0 and draw off of that. Then we look at the right 0 and we're drawing off of that. Okay. So what happens at -1/2? The multiplicity is 1. So we know it goes through. Right, so it goes through here. It comes up through the y-intercept. And then it comes down here to 3 at some point, and then it bounces off. All right, so let's kind of graph it and see what's up. So we have 2x plus 1 x minus 3 squared. So let's kind of look at it here. Where's our y-intercept? There we go, 0, 9, just like we said. We have our our x-intercept at -1/2, and it goes through there, right? So the end behavior towards the left-hand side, it's decreasing. And then on the right-hand side, we have 0 at 3, and it does bounce, and then it continues to increase. So what we did was, just given the information that we're given from the function, we kind of like pieced it together and said this is the general idea of what our graph would look like, and it worked out pretty nicely. Okay, so let's just do one more example of this, and I think that'll be it. Yep. So this time we have f of x equals x squared times x minus 3 times x minus 4. So the end behavior, we have 1x here, we have 1x here, and we have x squared. So that would be x to the 4th, right? We're just multiplying the leading terms for each of those. So that'd be x to the 4th. Because it's an even and it's positive, then it looks like a positive parabola towards the ends. Our intercepts, be careful here. Anytime you have an x or an x squared by itself, that's going to be 0, right? So 0. And then we're looking at the next one. What minus 3 is 0? That would be 3. And then x minus 4, that would be 4. Our y-intercept is f of 0. So we're going to do 0 squared. 0 minus 3 is negative 3. 0 minus 4 is negative 4. But 0 times anything is going to be 0. So this is going to pass through the origin for your y-intercept. Okay, multiplicity. So for our 0, that's multiplicity 2. For our 3, that's multiplicity 1. And for our 4, that's multiplicity 1. So if we're going to rough sketch this graph, let's go ahead and draw out our graph. Just do a rough sketch here. Well, our y-intercept is 0, which is good because our x-intercept there is 0 as well. And then we have one at 3 and one at 4. Okay, our end behavior. So let's do this in another color. Our end behavior on the outside of these last two points, it's gonna look like this and this, right? It resembles a parabola towards the end. That's the end behavior. So our multiplicity now, that's an even, right? Any even one bounces, so it bounces off of here. Whoops, that's gross. It bounces off of here, comes back to the next 0. It goes through here, and then it goes through the last one. So kind of like a W, looking like a weird W. If you want, you can go ahead and verify in Desmos. So we have x squared, x minus 3, x minus 4. And if we look at it, then definitely does look like a W. The end behavior is like a parabola, right? It's increasing on both sides. We have a bounce at 0, and we have 2 zeros where it goes through at 3 and 4. So it looks pretty much like what we sketched. All right, I forgot to do this on the last one, but it says just note where it's increasing and decreasing, and this is another good skill to have for calculus. So if we look at this graph, because it's wavy, there's going to be parts where it's increasing, there's going to be parts where it's decreasing. So remember, we read our graphs from left to right. So it's decreasing in here until it hits the line where it bounces. Then it's increasing. It's increasing all the way till we hit this point up here. Then we're getting smaller again all the way down to here. And then it's increasing again on the right-hand side. So not super important at this moment, but because we're looking at polynomial functions, it's a good time to talk about it, at least introduce it. Yeah, and it definitely plays a huge part in calculus once you guys get there. So kind of, you don't have to master this now, but take it in and kind of remember it because it's going to show up again. All right, that is it. Good job.